Okay, today we're going to cover two things. First is I want to cover higher order derivatives, and then we're going to cover one more differentiation rule that you need, which is called the chain rule. Okay, so first we're going to do higher order derivatives. Okay, so what if I wrote here f prime prime of x? What do you think that is? That is the derivative of the derivative of f. Okay, so let's say that f of x equals x to the fourth plus 5x cubed minus 7x squared minus 9x plus 3. Okay, let's find f prime, which is called the derivative of x, or you might now want to start calling it the first derivative of x. Okay, what would that be? Okay, you should be able to do this very quickly now. That would be 4x cubed plus 15x squared minus 14x minus 9. Okay, so now the second derivative of f, which is f double prime or f prime prime. It looks like a quotation mark, doesn't it? But it's not. It's two apostrophes, which I guess is a quotation mark, but I think you see my point, right? All right, so what would that be? That would be the derivative of the derivative of f. So that would be 12x squared plus 30x minus 14. And we could keep going as far as we want. You could do f triple prime. That's the third derivative of f. Or it's the derivative of f double prime. What would that be? That would be 24x plus 30, right? We could keep going. Now, it's going to start getting a little bit hard for your eyes to distinguish the number of primes. After 3, that's when people stop doing primes. And here's what we normally start doing. It's not a rule, you don't have to, but normally this is what people do. You'll put a 4 up here in parentheses. The 4 is for the fourth derivative. The parentheses is so that it doesn't look like f to the fourth power. Okay? What would be the fourth derivative of f? It would be 24, right? What would be the fifth derivative? It would be 0. What would be the sixth derivative? It would also be 0. And in fact, every derivative starting with the fifth one will be 0, won't it? So that's what is higher order derivatives. Okay? The derivative of f tells you the rate of change of f. The second derivative tells you the rate of change of the first derivative. And so on and so on. If you were doing a physics experiment and f was telling you the position of a particle, then what would f prime be? The rate of change of the position. What do we call that? That's called the velocity. And what would f double prime be in that case? It's the rate of change of velocity. What do we call that? That's called the acceleration. That's good to remember, okay? If the original function is telling you the position of something, then the first derivative is telling you the velocity, and the second derivative is telling you the acceleration. Okay? So in that case, what does it mean if the velocity is negative? It means the object is going backwards, right? And if the velocity is positive, the object's going forward. What about acceleration? If that's negative, what does that mean? It means the thing is slowing down. Can the velocity be negative and the acceleration also negative? Sure. That means the thing's going backwards and slowing down, right? Can the velocity be positive and the acceleration negative? Yes. That's in fact what you're doing when you pull up to a stop sign. You're still rolling forward, so your velocity is positive, but you're slowing down, so your acceleration is negative. Okay? Now, what about the other kind of notation with D's? That's called Leibniz notation, by the way. I'm not sure if I ever used that name with you. Trying to remember the spelling. It's German, and I don't remember if there's a T before the Z or not. I think there isn't, but I could be wrong. It might be TZ, but I don't think so. So I've used this from time to time in the lectures. If you have a function f, let's say f of x, then the first derivative would be df dx. Sometimes we write it like this. Either way is fine. The second derivative then, if you're using this notation, the second derivative is like this. You put a squared, no parentheses, a squared after the d on top, and a squared after the x on the bottom. Or if you don't, if you would like to pull the f over to the side, it would look like this. Hold on a second. Okay. Like that. The reason for the locations of the 2's being here and here is because of this. When I say f prime, I've been calling that the derivative of f. But the correct name, and I've said this one time in the past, the correct name is called the derivative of f with respect to x. So the reason for these 2's being here is because of this. You're doing the derivative twice, and it is with respect to x both times. That's why the 2's are located in those places. And the third derivative, if you're using Leibniz notation, would be d3f over dx3, and so on. Okay? So in the homeworks now, they might start asking you to find higher derivatives. Oh, here's an interesting one. What about sine? Let's say we start with this function, sine of x. Okay, so you know this now. What is sine prime? What is that? That's cosine, right? What's sine double prime? Well, that's the derivative of cosine, which is what? Negative sine. Now we're back to sine again, but we picked up a negative sign. So what would be the third derivative of sine? That's the derivative of negative sine of x, which will be negative cosine of x. What's the fourth derivative of sine? That's the derivative of negative cosine, which will be negative sine, which is sine. And we're back to the beginning again, and it starts looping around. So if I asked you what is the 64th derivative of sine, you would say it's sine, because 64 is divisible by 4. If I said, what's the 82nd derivative of sine? You would say it's negative sine, because 80 is divisible by 4. So 80 derivatives just brings you back to sine again. And so the 82nd derivative is 2 more derivatives after that, which would be negative sign. Okay, it's very interesting. And we also saw something interesting up here. For polynomials, look what happens. The degree goes down by 1 every time you do the next derivative, right? So whatever the degree of the polynomial started with, you can calculate that many derivatives before what happens, before all of the derivatives start equaling 0 after that. Okay, so that's higher order derivatives. It's a simple topic, but it's something that I've been saving, and I wanted to make sure that we covered it at some point. Okay, now one more rule of derivatives that you need, the chain rule. This is an important one, okay, to add to your list. And then I think you'll have all of the basic rules of differentiation. So the chain rule is how to do the derivative of a composition of functions. So let's say we have f of x and g of x. And then you plug g of x into f. And let's say you want to find the derivative of that with respect to x. Okay? How would you do that? There's a rule for it. It's not obvious. So I'm going to tell you what the rule is. You first calculate the derivative of f. And into that, you plug the function g of x. And then you multiply times g prime of x. This is super important. So let's practice using that. Let's find the derivative of sine of, let's say sine of x squared. How about that? So just so you can keep track of this. So here's sine is the function f. So I'm going to write f of x equals sine of x. Okay? And g of x equals x squared. And what I have up here is f of g of x, and I want to find the derivative with respect to x. So let's follow what the chain rule says. It says calculate f prime. So what's the derivative of sine? It's cosine. And into that function we plug in what? G of x. So I'm going to get cosine of x squared. And a lot of people might think at first that that would be the whole answer, because the derivative of sine is cosine. So it makes sense to say the derivative of sine of x squared would be cosine of x squared. But that's actually only part of the answer. Then you have to multiply times g prime of x. And what's that? It's 2x. So there is our answer. I would write 2x cosine of x squared is how I would write it. Okay. Let's do the derivative of cosine of 5x. So f of x is cosine of x. G of x equals 5x. So the derivative will be, what's the derivative of cosine? It's negative sine, so we'll have negative sine of, and into there we plug in g, which is 5x, and then times the derivative of 5x, which is 5, And so what do we have? We have negative 5 sine of 5x. Okay? Let's do one over x squared plus 5. We want to find the derivative of that. Okay? You don't have to know the chain rule for this. You could use the quotient rule, right? Because that's a quotient, isn't it? You could go derivative of the top times the bottom minus the top times the derivative of the bottom divided by the bottom squared. And so what would we end up with? Negative 2x over x squared plus 5 squared. So that's certainly one way to do it. There's nothing wrong with that. It wasn't particularly difficult. Okay, but I just want to show you that now that you know the chain rule, there's another way to do this problem as well. You could write it like this: x squared plus 5 to the negative 1 and you could use the chain rule, and here f of x is x to the negative 1 and g of x is x squared plus 5. So what would we get? We would get negative 1 times x to the negative 2, except, whoops, it's not x to the negative 2, is it? How am I getting that, by the way? It's because I'm taking this and I'm bringing it down, and then I'm subtracting 1 from there. That's where the negative sign in front is coming from, and that's where the negative 2 exponent is coming from. I'm just using the power rule. And then what do? I plug into that g of x, and then I multiply that times the derivative of x, derivative of g, which is 2x, and I end up with the same answer, negative 2x over x squared plus 5 squared. Okay? Using the quotient rule was maybe a slight bit faster, but I just wanted you to see that you could do that problem without the quotient rule if you know the chain rule. Let's try this one, just to make you remember e to the x and natural log of x. Remember what I said about those? We're going to do the derivative of e to the negative x squared. Let me just remind you about these two functions. I'm going to write this in blue. I said e to the x and natural log of x. I said what their derivatives were. I'll remind you in a second. I said that we will look at those two functions really in depth in Calculus 2. But I know that you've seen them before, and so there's no reason why you can't know their derivatives. So I went ahead and told you their derivatives now. And what I told you was that the derivative of e to the x, whoops, there should not be equal sign yet. Derivative of e to the x is itself, and the derivative of natural log of x is 1 over x. And you're going to want to remember those, especially the e to the x. Okay, so let's do this problem over here now. The derivative of e to the negative x squared. So f of x is e to the x, and g of x is negative x squared. And g of x is being plugged into f of x. So we have e to the g of x. Okay, so how do we do the derivative? So the derivative of e to the x is e to the x. But up here, I don't put x, I put g of x. And then what do I do? Because of the chain rule, I multiply by the derivative of g, which is negative 2x. And so our answer is negative 2x e to the negative x squared. Okay, let's do the derivative of the natural log of 4x cubed minus 2x squared. So f of x is natural log of x. G of x is 4x cubed minus 2x squared. So how do I do that black derivative? I write 1 over g of x times the derivative of g of x. So what do we have? We have 12x squared minus 4x over 4x cubed minus 2x squared. You can do some simplifying, but that's not the point right now. The point right now is the calculus. I want you to see that that is how you do the derivative. Okay? If you do want to simplify it, it simplifies by a 2x, right? And so we could write 6x minus 2 over 2x squared minus x. Okay? We're going to do one more question. Okay, right there we have in blue the graph of cosine of x squared. And in red is the tangent line at x equals 1. And the question here is to find the equation of the tangent line. Okay, so what do we need? We need a point and the slope. Okay, so what's this point of tangency right there? That's when x equals 1. So what's the y value? Can you see there? It looks like 1/2, doesn't it? It's very tempting to just go, oh, it's 1/2. Okay, be careful. It's not. It's close to 1/2, but it's not. Don't just make assumptions. Okay? How do you actually find the y value? You find the y value by plugging in the x value, don't we? What's f of 1? It's cosine of 1 squared, right? Which is cosine of 1. That's the exact answer, which means it's the best answer. I'll go ahead and write down the decimal approximation. But I just want to make it very clear that an exact answer is better than an approximation. The cosine of 1 radian is approximately 0.54. Okay? But exact answer is better than an approximate answer. So I'm going to write 1 comma cosine of 1. Okay? Now how do we find the slope? We find the slope with the derivative, right? So let's find the derivative of f. So f is cosine of x squared. So first you do the derivative of the outside, which is cosine. What's the derivative of cosine? It's negative sine. So we have negative sine of x squared. And then you multiply times the derivative of the inside. The inside is x squared. And the derivative of that is 2x. So negative 2x times sine of x squared. Okay, that's the derivative at any particular x value. We want the derivative when x is 1, so let's plug in 1 into there. We'll get negative 2 sine of 1. You agree with that? So that's the slope. If you want to know a decimal approximation, that would be approximately negative 1.68. So that line is y minus cosine of 1 equals the slope times x minus 1. That is the exact equation. If you would like to take that cosine of 1 and put it to the other side, you're welcome to do that. And then we would get y equals negative 2 sine of 1 plus cosine of 1. That's the exact equation. Now, if they ask you for an approximation, then we can go ahead and use these decimals here. And we would have y equals negative 2 times, oh, sorry, no, I've already multiplied by the negative 2 when I wrote down the decimal approximation. So it would be y equals negative 1.68 times x minus 1 plus 0.54. And that would be our answer. Of course, you could distribute the negative 1.68 if you would like to. We get negative 1.68x plus 1.68, and then plus another 0.54, which would be how much? That would be 2.22? I think so, but let me just double check my arithmetic. Yep, 2.22. Okay? So that's the chain rule. Very important. Comes up so many times. So many times. Okay? And that's it for today.